Chemistry is also a rich source of related rates problems, in particular the ideal gas law that states that the pressure times the volume of a gas will always equal the number of moles times the ideal gas constant times the temperature in degrees Kelvin. This is a law that will always be true. If we increase the pressure, the volume will go down. If we increase the temperature, somehow the pressure and volume must increase as well. There's always this balance. We're going to consider the example where 0.1 moles, so that's our N, are going to be held in a piston, and the temperature is going to be held constant at 0 degrees Celsius or 273 Kelvin. So our temperature is going to be constant. The piston is going to move to decrease the volume from 3 liters to 1 liter over 60 seconds. What are we looking for? We're looking for the pressure halfway through this process. So we have no information about the volume. We have information about the volume, and we're interested in what the pressure is going to do as a result. Okay, let's tease this statement out first. We're going down 2 liters, going from 3 liters to 1 liter, over 60 seconds. So the best way to interpret that is that this would be the rate of change of the volume in liters per second, check the units, and that would be negative 1/30 liters per second. So if we go for 60 seconds, we get 60 times that, we'd go down by 2 liters. Okay, so this scenario actually gives us the identity that we want to start with. This is something that's always true. So PV equals N, R, and T. We're now going to differentiate both sides of that with respect to time. Now this isn't always true, but this right-hand side has a constant number of moles, a constant ideal gas constant, and because the temperature is held constant, this wouldn't always be true, but it's true for the scenario, these are all constants, so the derivative on this side is simply going to be 0. The other side's a little more complicated. In the back of our minds, I'm going to put a little bracket T here and a little bracket T here to indicate that pressure and volume are changing. As I shrink this volume, I'm moving this piston, the volume's going down. The pressure must increase to compensate. So both of these are variables that change with time. If we take the derivative of the first times the second plus the first times the derivative of the second, as the product rule would tell us to do, we're going to get this expression here. And this is our relation between the rates of volume and pressure change. And what do we actually want to solve for? We want to solve for the pressure halfway through this process and at what rate is the pressure changing at this time. In fact, we're almost halfway to the pressure rate, so let's calculate that first. V times that is going to equal pressure dV dt. And so the rate of change of pressure is going to be P over V dV dt. So this is the rate relationship that's always true. Now we want to know when that's what that value is going to be halfway through this particular scenario. And we still have to find clearly the pressure when we do that. So we'll move that all to the next page to calculate the pressure halfway through and then the resulting rate of change of pressure. That's our related rate. And we also have PV equals nRT. And at the halfway mark, the volume is what we know. It's going from 3 down to 1, so halfway through it'll be 2 liters. Well, if we have 2 liters, then pressure will be nRT over V. We can start filling in values. We had 0.1 moles. R in the units we're using is 8.31. Our kelvins are 273, and our liters are 2. And so our pressure here can be calculated as 113.4, and the units here would be kilopascals to go with this form of R. Okay, so that's our pressure. If we want to know the rate of change of pressure, we're simply going to fill this in. So there's 1, we'll bring that up into here. And so we'll have 113.4 divided by the volume, which we said was going to be 2 liters, times the rate of change of the volume, which we said was 1/30th, but negative. Working all that out, we get negative 1.89, and the units for pressure against time will be kilopascals per second. We did all this over 60 seconds, so the time units were seconds. And that pretty much concludes the example. We can calculate static values. That's classic stuff that you would have seen several years ago. And then we can also calculate through these relationships between the rates what the rate of the pressure change would be if we know how the volume is being changed over time.